Okay, so you can see this on your screen, right? So you can
हाँ
see
सर
this
लगा जाते
on your screen. Yeah. So basic summary of what has been done till now. You see, we started off our course of lectures with the basic assumptions on stellar structure, right? Regarding sphericity, isolation, composition, okay? And then we talked about the most basic of the stellar structure equations, the equation of continuity, and mass conservation. And I have written in red pen, you can see the derivations. This means these sections have derivations in them. After that, we talked about the next very important topic of hydrostatic equilibrium, and it was derived from the equation of motion. And then, since we are talking about a gravitationally bound star, so it is very important to know that the pressure will be much higher in the interior of the star compared to its outer parts. And using this equation of hydrostatic equilibrium, we can make a very rough estimate of the average pressure and also make a lower and upper limit of central pressure, get an estimate of it. In that lecture I talked about the lower limit, and maybe you can do it as a homework about how to find the upper limit as well. You can think about it. In fact, this rough estimate of central pressure is closely related to the rough estimate of central temperature as well, which we can obtain from virial theorem. That was the next topic. And in this lecture, we derived virial theorem from hydrostatic equilibrium. There are other derivations of virial theorem as well. A generalized derivation, we avoided it. Instead, we started with the equation of motion path, then moved to derivation of hydrostatic equilibrium equation, and then from there we derived the virial theorem. And afterwards, I very much spent some time discussing the various consequences of the virial theorem when applied to star. Okay. Then we talked about very interesting application where using virial theorem we saw that for the same mass stars the denser star is hotter. This was a very interesting and important derivation. After that, we talked about the equation of local energy conservation and luminosity. And then we talked about whether it is possible to have both hydrostatic and thermal equilibrium at the same time. So these were the contents of the first two lectures. Next, on the third and fourth lecture, again, we talked about the what is an important topic, also known as Newtonian theory of stellar evolution. We talked about the dynamical stability of a star and how to arrive at the condition, adiabatic constant related condition, and we arrived at that relation using the equations of hydrostatic equilibrium and then virial theorem. We also used the we also assumed that the star that we are talking about has a follows a polytropic model, if you remember that pressure and density relation. So assuming that, we arrived at a condition for dynamical stability. Afterwards, we talked about the concept of pressure ionization, now which was very, what can you say, it was very uh, you can say it was very common. I mean, common in the sense that it was bound to happen. If a star is gravitationally bound, and we know that the star originally forms from the gravitational collapse of a big, very big giant cloud, Then, as the cloud collapses, the atoms and molecules inside the cloud will come closer and closer and closer. And at a time will come when the atoms might be squeezed onto each other. At that time, the nuclei and the electrons will get separated from each other. So the electrons will leave their parent nuclei and become free, thereby forming a sort of electron gas. This was the concept of pressure ionization. Okay. Now, after that, we talked about the global and local thermodynamic equilibrium. What was the importance of it? At a first glance, you know that we just talked about it, right? That a star, its central temperature will be higher, and that of the outer temperature will be lower. Say for the sun, the central temperature is of the order of 10 to the power 7 Kelvin, whereas the surface temperature is of the order of 6000 Kelvin. So what does this mean? At first glance, it means that the sun is not in a state of global thermodynamic equilibrium. Why? Temperatures are different, right? But even so, if we consider a very small part, and we have seen that, and if we consider a small part and assume that there is a local thermodynamic equilibrium, then using these conditions, if we derive various relations, they are found to be correct, or they are found to follow the observed experimental patterns, experimental data. And this was the logic behind our consideration of local thermodynamic equilibrium. After that, we derived a very important relation known as pressure integral, and then we used that relation to derive the equation of state, or basically the expression of pressure for a perfect gas for both non-relativistic and extreme relativistic limits. This was a very simple and interesting derivation. After that, we talked about the derivation of ideal gas law. Again, this was an equation of state for non-relativistic classical particles. You can do the relativistic classical particle derivation by yourself as a homework, and you will be surprised to know that you will get the same old gas law even for the relativistic classical particles. After that, we talked about mixture of ideal gas, right? And then we introduced the concept of mean molecular weight. And then these were all classical discussions, right? Whether be it non-relativistic or relativistic. They were all classical discussions. And then we started to talk about the quantum regime. And so we talked about the quantum mechanical description, the three-dimensional possibilities of Bose-Einstein and Fermi-Dirac statistics, the two types of possible statistics. And then we talked about the complete electron degeneracy. Okay, we derived it. And this was done up to our fourth lecture. Now, in the fifth lecture, again continuing from our previous lectures, we talked about the Pauli's exclusion principle and derived at a condition for degeneracy, onset of electron degeneracy. How do you arrive at it? Now we used the concept of de Broglie wavelength. If you remember that, we used the concept of de Broglie wavelength comparison to arrive at the condition of electron degeneracy. And also you can use the concept of energy, Fermi energy. They were the two types of onset of degeneracy discussions we did. And then very brief discussion on white dwarf stars, where the electron degeneracy plays a very crucial role, we discussed. Now in case of neutron stars, the neutron gas will play sort of play a very important role, quite similar to the white dwarf gas. But again, neutrons are different particles compared to the electrons. So that's why the white dwarf and neutrons will have very different properties in itself. Although there will be some similarities, but the differences will also be very interesting to know. And I will talk about them more briefly when we talk about the neutron stars later in our course. Now, after that, we again revisited our complete electron degeneracy scenario, and then we derived we or I can say we arrived at the, we derived third derivation. It was the third derivation of how to obtain degeneracy scenarios, and we discussed both non-relativistic and extreme relativistic cases. After that, there was a very brief discussion on complete and partial degeneracy of electrons and what are the various important roles played by this degeneracy in stars. And then, till now, you see, we are talking about gas and electrons, right? So, what about the photons and neutrinos? For the time being, I am not talking about neutrinos, but as for the photons, I talked to you in this lecture, and there we derived the equation of state of photons, or basically, we derived the relation for radiation pressure. And finally, we obtained an expression for the pressure of a mixture of gas and radiation. Now, in the last lecture, I talked to you about the equation of state regimes, various equation of state regimes, and I also discussed about the equation of radiative energy transport and the equation of energy conservation. Also, we discussed about the equations of stellar structure, about them. If you remember, I talked about the Russell-Vogt theorem and then about the absorptions. What are the various sources of absorption and how we can characterize them or understand them in terms of empirical relations. We talked about the Kramer's opacity rule, and then there was a very interesting discussion on actual usage of these first order differential equations, how to use them in the simplest way possible and arrive at relations which can tell us or which can give us physical picture inside the stars. And there we used the scaling relations for the main sequence stars, and we obtained very interesting relations. After that, we talked about the convection. So we talked about convection as well, along with radiation, and we derived the Schwarzschild stability criteria. And then there was a very brief discussion on the three timescales of stellar evolution and their importance. Okay, so this is what we have done up to our seventh lecture. Okay, now you asked me if you have any questions.